All right, pre-calc. Right now I want to talk through this problem that we have here that has to do with deriving the formula for the ellipse. So we started this one in class, but I'm going to go back to the beginning. Over here, we have our setup. We already determined that for any ellipse, the sum of those two distances from one focus to any point on the ellipse, that sum of those distances will be the same as the length of our major axis, which we described as having a length of 2a. So with that in mind, right now I want to help us derive the formula that we talked about in class. We know that eventually we should get to this extremely simple, beautiful formula that says that x squared over a squared plus y squared over b squared is equal to 1. It's simple, and it tells us all this information that we want to know about the ellipse. For example, it tells us what the length of our major axis would be, or our minor axis, because we can always just double the a to get 2a. I also want to keep in mind another piece of information we found. When we took the string and dragged it to that bottom or upper vertex, we saw that those lengths were the same. So since the whole thing is 2a, each individual length is just a. And that helped us see this right triangle and the relationship between a, b, and that distance to our focus, c. And that's how we got the somewhat annoying inverse Pythagorean theorem that says that a squared is equal to b squared plus c squared. I want to keep this in mind because it'll be useful later on. How do I know it'll be useful? Because I've done this before. So now let's look over here at d1 plus d2. I'm going to start here, but slowly turn this into our formula. So first, I'll find the distance between these 2 points, x, y, and our focus, c, 0. Now, that's already written out for you right here. X minus c squared gives us that horizontal length, and y minus 0 squared, or just y squared, gives us the vertical length. The same is true for our other distance. Instead of x minus c, we have x plus c because our coordinate is negative c. So really what I did in my head there was x minus negative c, or x plus c. And then finally, we'll have y minus 0 again, or just y squared. That's all equal to 2a. And now it's time to do a lot of symbol manipulation. As we discussed in class, the best way to get rid of a root when we have an equation with 2 square roots is to move one to the side and then square. So I'm going to do just that. I'll subtract this entire term here from both sides, and I'll get square root of x minus c squared plus y squared is equal to 2a minus, and then that larger radical, x plus c squared plus y squared. Now, I'll square all of this. My right side will become just x minus c squared plus y squared. And then my left side will become 4a squared minus 4a, and then the whole radical. And then plus the entire radical, x plus c squared plus y squared. Now, already, there's a way for us to simplify what looks pretty complicated. I'm going to subtract y squared from both sides. And now I'm going to expand the x minus c and x plus c squareds because I know that there are terms in there that'll cancel out. This one will give me x squared minus 2xc plus c squared. And this one will give me x squared plus 2xc plus c squared. And again, we can cancel out our x squareds by subtracting x squared, and cancel out our c squareds by subtracting c squared. So I'll do a little more consolidation by combining my two xc's. So I'll subtract this one over here, and I'll end up with negative 4xc is equal to 4a squared minus 4a root x plus c squared plus y squared. Ooh. Okay, so we've done a lot of work here. We still have to square it one more time to get rid of this other radical, but let's do one more simplification. I'm going to divide this entire equation by 4. That's going to eliminate this, that, and that 4. And now we're left with negative xc is equal to a squared minus a with this whole radical. Now, if you don't enjoy working with negatives, we can move a couple things around here. So I'll add this radical to both sides and then add the x plus c to both sides. And that will give us a with our entire radical expression is equal to a squared plus xc. And now, let's square it. So this is going to end up giving us a squared times quantity x plus c squared plus y squared is equal to, then squaring the entire right side, we'll have a to the 4th plus 2a squared xc plus x squared c squared. I'm going to expand one more time and then distribute this a squared onto all of those terms inside. So first I'll expand into x squared plus 2xc plus c squared plus y squared. I'll just, let's just copy that. Was that any faster? And then we'll get a squared x squared plus 2a squared xc plus a squared c squared plus a squared y squared is equal to a to the 4th plus 2a squared xc plus x squared c squared. And let's cancel one more time. We can get rid of the biggest terms, the 2a squared xc's, and that seems to be it. So now at this point, you're probably looking at this and you're thinking to yourself, how is this any better? I feel that, but I do want to point out that there are still some moves that we can make. For example, let's keep our destination in mind. We want to end up with an equation where our x's and y's are all on the same side. So right now, I'm going to put my constants on one side and my x and my y's on the other side. So let's see, I'll move the x squared c squared to the other side. X squared c squared. I'll move my a squared c squared, so that's constant, to the other side as well. So that will be subtracted, a squared c squared. Now there's a pattern here that I want to point out. We have a squareds in a lot of terms, and we also have this a squared minus c squared business going on here. And I do want to now bring us back to our inverse Pythag. One thing that I want to point out is that if a squared is equal to b squared plus c squared, then isn't it fair for me to say that a squared minus c squared is equal to b squared? All I did there was subtract the c squared from the other side. But now, if we do a little bit of factoring, we can actually bring the b squared into the equation, which is what we need. So I'll factor out an x squared here and turn this into a squared minus c squared. And similarly, I'll do the same thing here. This becomes a squared minus c squared, which we just said was b squared. So this becomes x squared b squared plus a squared y squared is equal to a squared b squared. And then since our equation is all equal to 1, that's where we want to be. We want it to all be equal to 1. I'm going to divide both sides by a squared over b squared, or by a squared times b squared. That gives us x squared b squared over a squared b squared plus a squared y squared over a squared b squared is equal to a squared b squared over a squared b squared. And look at how these terms cancel each other out. And we are left with x squared over a squared plus y squared over b squared is equal to 1. And that's the equation for our ellipse. So what did we just learn? Well, we learned that by starting with d1 plus d2 is equal to 2a, and by working our way down u really logically, and by using the Pythagorean pattern that we have, now we know exactly where our equation for our ellipse comes from. And you can even use it now on problems like these. If you take a look at this problem right here, this is the equation for some ellipse, and we can learn a bit more about it by turning this 25 into 5 squared and this 16 into 4 squared. And now this tells us this must be an ellipse, and it's an ellipse with an a value of 5 and a b value of 4. And so if I want to graph this ellipse, I know that 5 units away from the center on either side left or right, and 4 units away on either side up or down, those will be my vertices, because I have this a distance of 5 and this b distance of 4. And furthermore, I can find my foci, because I know that my foci are around here somewhere. They have to be maybe around here, or maybe around here, and I can find those exact values by using the formula that we already found. We know that a squared is equal to b squared plus c squared, and c is our distance to our foci. And so since a is 5 and b is 16, or b is 4, we can solve for c. In this case, c is 3. So our foci lie at 3, 0, and negative 3, 0. And that's our general form of the equation for the ellipse. I think this is enough to help you get started on some problems of your own. Now, there is a little bit more to solve. For example, this equation only works for ellipses that are centered at 0, 0. But I'm confident that you can then extend this to figure out how the equation works for ellipses that are centered at different locations. Have fun.